Okay, hello. I'm once again here to solve an interesting question, now back to organic chemistry. So let us take a look at this question, which I took from RI's 2018 prelims. And so let us take a look. Many carbonyl compounds have pleasant fragrances and are widely used in the perfume industry. So this one has a warm floral jasmine scent. Okay, interesting. Analog of methyl jasmonate, a key component of jasmine oil. Okay, so this hedione can be synthesized from methyl jasmonate via the reaction scheme. Okay, so let's see what happens. Okay, the first step, replacing this carbonyl with this functional group over here. And then the next step would be hydrogenation, right? Reduction via reducing the CC double bond. Then after the acid hydrolysis, and then lastly esterification. Okay, so first state the reagents and conditions for step 2. So as I mentioned previously, step 2 is a reduction of the CC double bond. So it will be H2 Ni heat, right? Alternatively, you can use or H2PT or PD. Okay, and you don't have to heat if you use a palladium or platinum catalyst. So hence explain why the carbonyl functional group was converted into another functional group in step 1 in the reaction scheme. So in this case, it's very obvious that the carbonyl group would also have reacted if it was directly step 2 was applied to it, which is H2 Ni heat, right? What will you get? You actually get secondary alcohol, right? So that is not desirable. Why? Because we want to preserve the carbonyl functional group. So we can express our answers like this in two parts. So firstly, state what we are trying to avoid. So the carbonyl group or the ketone functional group would have been reduced by H2Ni heat to a secondary alcohol, which is not desired as the product kind of keeps the ketone group intact. Hence, the ketone is converted to another functional group, so which does not react with H2Ni heat. So that only the alkene group will be reduced. This functional group is then converted back into the ketone in a subsequent step, right? Which is step 3, where it's actually the hydrolysis of this group to form back the ketone. So what type of reaction involving the ester group occurred, as I mentioned already just now? It is simply acidic hydrolysis. So and then step 4, basically we are going from this to so it's obvious there's an esterification. So esterification, we need the alcohol to react with the carboxylic acid group. So CH3OH, and you need Kong H2SO4 catalyst, right? Because you are not using acyl chloride, you are using a carboxylic acid here, and heat, definitely. So let us take a look now at compound and a constitutional isomer of methyl jasmonate. Okay. So how does it differ? It differs. Oh, it is a Is it a cis trans? At first I thought it was a cis trans, but actually looking closely, the position of the double bond is different. Right? So it is actually a structural isomer. So instead, why NABH4 reduce the carbonyl group but not the alkene group as we expect? So now they ask you to explain why. So it is quite easy, because the NABH4 produces the hydra ion, which is attracted to electron deficient sites, right? The hydride anion, being negatively charged, is attracted to sites with electron deficient sites with partial positive charge. However, the alkene group is electron rich, right? We learned, and repels, and the pi bond repels the negatively charged hydride anion, hence hydride reducing agents like NABH4 cannot reduce the alkene group. Oops, what happened? I think I accidentally activated strike through. Okay, let me just get rid of that. Okay, good. So that's a simple question to answer. And my thought process behind answering this is to thinking, what is the mechanism by which the reduction is occurring, which is in this case the production of the hydra ion being the reacting species, right? So why hydra ion does not react with the alkene group but it reacts with the ketone group, right? So now we see in step 2 the reaction of O with aqueous sodium hydroxide is known to occur as follows. Okay, so basically this is alkaline hydrolysis. First step involves the nucleophilic attack of the hydroxide ion on the carboxyl carbon. So the carboxylic acid carboxyl carbon, right? Let me draw it out so that you can actually see. Actually, this mechanism is a standard, sort of a quite rather standard hydrolysis mechanism, but unfortunately it's not in the H2 syllabus. So even though I know this mechanism, I'll pretend as if I don't know and work it out based on the prompts. And what is the compound? The compound is COOCH3. Okay, so what are we given? We are given that the first step is the nucleophilic attack of the hydroxide ion on the carboxyl carbon to form a tetrahedral intermediate. So we know that this group does not immediately leaves, because there's a tetrahedral intermediate, and it's not even a transition state complex, it's an intermediate. So all the bonds must be sort of preserved. So the only bond you can break is the pi bond of the double bond. It also makes sense because the pi bond, right, is weaker than the normal sigma bond. So it's most likely that the pi bond will break. Okay, so this is likely to be a slow step. But actually, stating the slow step is probably not required here. So the oxygen gets the pi bond electrons, so it has a negative charge now. And the OH group now attaches over here. So this is the tetrahedral intermediate. And now the second step, so we would just copy that. Okay, involves the formation of a carbon-oxygen pi bond and the leaving of a methoxide ion. So this is the reforming of the pi bond, and the methoxide ion leaves, right? So this bond has to break to liberate this methoxide ion, right? So this should be like this. OH plus CH3OH. So now, okay, third step involves the protonation of methoxide ion by the carboxylic acid. Okay. Protonation of the methoxide ion, so it's very simple. This sorry. So the methoxide ion deprotonates the carboxylic acid. And what do we get? It is simply a carboxylate anion and a protonated alcohol. So one way to check whether you're correct when it comes to charges is that neutral reactants must definitely result in products with an overall sum of the charges to be 0. Okay, so that is indeed so, and so we are correct. And okay, I made a mistake. They say that you should represent compound O as RCO2CH3. I actually drew out the entire compound, but it's okay. Probably won't be penalized. And part 3 suggests the structure of compound P and name the mechanism of the reaction in step 3. Okay, let's take a look now at step 3. Okay, okay, normally if you add Br2, we expect it to add 2 Br atoms across the double bond, but that is not so. There's only 1 Br atom here. So what has changed? So okay, we can ignore the sodium cation, C12H19O3 minus. So what happened? There is an addition of a Br plus. Okay, so this calls into mind the first step, right, which is of a double bond, and then the bromine atom. Basically what you are doing is you are adding a Br plus, correct? Then after that, right, nothing seems to happen. But actually, if you are to analyze this, right, in a stepwise fashion, right, analyze the reaction in a stepwise fashion, you'll soon discover what will happen. Yeah. Having a lack of space here. So okay, first the Br2 will approach. Then what will you get? Okay, we are not sure which carbocation is more stable. Okay, because both of them are secondary carbocations, irregardless of which carbon atom the Br bonds to. So what do we observe here? We observe here that there's 2 oppositely charged sites next to each other. They can attract and form a bond using a lone pair of the oxygen atom. So what do you get? You get something that looks like this. So this is the structure I'm going to propose for P, right? And does it fit the formula? Yes, it does, because I only added 1 Br plus to it. So that will be my suggested structure. Okay. There's another potential suggested structure with the Br being on the other, being added to the other carbon atom, and the O being added to this carbon atom, thus forming a 6-membered ring. Right? This is a 7-membered ring. Okay, so 6-membered rings have some special stability, so it could also be possible that the 6-membered ring would be formed. Okay, so I name the mechanism of the reaction. This is electrophilic addition. Okay, electrophilic addition. Okay, so I hope that this today's short video has helped you, right? I was solving this question on the spot. So if there's anything unclear, you can just comment in the video, and yeah, I'll see whether I can address your concerns. Okay, thank you.